Let me welcome Eric and Jean for the talk about Tor and give them a warm round of applause. Thank you.
Good morning, everybody. So we are going to present you our work on the Tor network, or more specifically on dynamic cryptography backdoors, and how to apply it to try to break some encrypted network. So it is a joint work with Sean and our colleague who now is back to Tanzania, the University of Tanzania. So here is the agenda, and most of the time people speak about breaking cryptography, but in fact most of the time we think about using huge time-consuming exhaustive search, which is of course for modern cryptographic system quite impossible or totally impossible. But most of the time we observe the fact that we have the situation of armored door on a paper or cardboard wall. So why bother to try to break the door if you can go through the window, find the key under the carpet, or even crush the wall? So we have to take the environment in a very broad sense, the operating system, the users, the network architecture, the protocols, to determine whether it is possible to use and exploit them to bypass cryptography. Everything is, of course, in a context where we all suffer from breaks of protocols, of tools that are imposed by standards, by organizations, and we have to work with them. And maybe more concerning is the fact that we all are suffering from some sort of standardization of mind. If you consider, for example, the development of cryptographic IPA, it is very difficult to try to develop without considering those norms, at least for some products. So in fact, we have to remind that the aim is not to have the key or to break the system in an academic view. The very final aim is to have access to the plain text. So in fact, we have extensively worked on what we call dynamic cryptographic backdoors, mostly implemented through malwares. Otherwise, we can do the same job but with trapdoors. And it has been possible, it is a few results we obtained to bypass, for example, IPsec-based encrypted network. You may use Tempest or not, it's not the issue. And for example, we have applied these techniques to break some military IP encryptors. In this respect, most of them are badly implemented. And what is very important to stress on and to keep in mind, and everything has been tested, or we like to go from theory to practical stuff and to verify that everything works. So all these attacks are very efficient. So now we are going to explain how it is up to us. It is possible to apply this kind of techniques over a network, encrypted network like Tor, or any other network of this type. So the starting scenario can be either an undemocratic country. We want to monitor, not to block. The aim is not to block the network. It's quite the contrary. Just to monitor and to survey all the political opponents. May it be outside or inside or outside the country, or any small group of bad guys. So, a few elements I think that are important to keep in mind. More and more, with the evolution of regulation, national regulation in Western countries, the use of malware is now something well recognized and accepted. And I have no exception in mind, from France to United States and Germany or United Kingdom. Now it is well accepted that police forces, intelligence forces can use, without a restriction, malware. So it is not a dream, it would be more a nightmare, it's reality. And they are beginning to develop many capabilities in this respect, and probably China is among the most advanced country in this area. So we would like to present our attack not like a single attack, just deploying malware. No, from an operational point of view, from a tactic point of view, it's not a good idea. In fact, we would like to present an attack which is in fact more related to the way military are thinking, and to organize a coordinated multi-level attack with small surgical strike in order to combine to a very final effect. And I had many discussions with officials in different countries, and they say, well, if you manage to break at least 1% of the traffic, it's already a success. So, no matter if the attack is very efficient or only efficient, but if you already manage to have this success rate, it's already a success. Of course, we think it's possible to do far better. So here is the agenda. So Sean will present all the network part. I will try just to recall some part about dynamic cryptographic trapdoors. So in fact, it is very interesting to notice that most of the implementation rely very importantly on the environment and the operating system. For example, under Windows, I have only a very few exceptions in mind. They all rely on the Microsoft cryptographic API. You have just to hook this API to do what you want. You can modify algorithm in memory. For example, we managed to scan for SBox of the AES in memory and to replace those SBox with weak SBox that, of course, the attacker knows in advance. You can turn between modes. You can do many things. And the word dynamic comes from the fact that, in fact, you can play it only during a limited window of time. Just stop, then come back to the attack. It's fully customizable. So, of course, if you consider the static security, the mathematical security, the algorithm has not been modified, has not changed, since everything is in memory. So, for example, here we use the cryptgen random, which is the most common used function to generate, for example, initialization vectors. So here, for example, we want that the malware modifies the cryptography in memory between noon and 2 p.m. So it is part of a small part of the malware we have developed. So here we fix the message key for a limited period of time. So why fix the message key? Because in this case, all the messages that are going to be encrypted will be parallel ciphertext. It means that it is easy to detect them. Among many encrypted text, you can detect them in a polynomial time and break them as well in polynomial time. Just the fact to reuse, to fix the IV. So we have developed a cryptanalysis library exploiting this fact, and you will be surprised how many encrypted traffic can be partly broken with applying these techniques. Of course, we are considering stream cipher modes. So how to do that when you have, for example, ECB or CBC mode? Well, that's where there is a very interesting point because in fact, since the contest of the NIST, National Institute of Standard Technology, to promote the AES, in fact, they impose some sort of standardization of mind to develop around cryptographic library. As a consequence, many developers are writing their library in the same way, most of the time. So there is some sort of standardization of mind. So if you explore this, you can do many things. You can change many things in memory with malware in order to weaken the cryptography. So, for example, here, you have during the cipher init, you have a byte which defines a mode, and then you just change a few bytes in memory and you switch from one mode to another one, which is actually very interesting. So, how to use that? So first, I would like to stress on the fact that we do not have anything against Tor. This is not the issue. Actually, at the present time, it is the only available network of this type. We have made experiment on other, well, non-public networks, so it is, of course, impossible to publish. So I think that it is a good field of experiment. But once again, our aim is not to say to have something against Tor. So, well, you will find everything where I explained the library, the Tor extend library, the different data are available either on the wiki of the conference or on this link. So Sean has developed a very interesting library. You have the Google Earth map of everything. So, in fact, we have tried to consider the Tor network as a critical infrastructure. When you deploy some brick, in fact, you don't know whether you will have local weakness or, and how to exploit them. So, in fact, it is not the Tor technology in itself that we analyze. In fact, it is the fact that we explore the fact that it is deployed by volunteers, using their own security, computer security, and of course, using weak protocols. So, I won't recall how Tor works. There was a talk yesterday. So just remind that in fact you have to find a circuit of 3 nodes, 3 onion routers, randomly, every time you want to exchange secretly and anonymously. So you have here, very quickly, the key negotiation. In fact, there is a first level to negotiate a secret key and to make sure that all the 3 nodes have the same key. So about the previous attacks, there are many attacks, so I have just mentioned some of them, but of course you will find everything on the Tor Foundation blog. I think they are referencing everything. So, in our attack, in fact, we try to work at a very high level and low level at the same time. So first, you have to make intelligent step. You have to try to have as complete view of the network. How many onion routers, hidden relays, and so on. So, in fact, in this respect, our attack just follow what military are doing. Intelligent step, planning, and conduct of maneuver. So, many people say, okay, we have broken Tor. No, once again, it's not the issue. It is the deployment of Tor. Because the core concept, up to me, is rather sound and elegant, but it is deployed on a very imperfect world. Weak protocols. We also use some protection mechanism that we have turned against the network. And of course, every volunteer is free to use his own security rules, and just imagine the same in a large company where everything is free to choose his operating system, to secure or not his computer. Well, it will be a nightmare, honestly. And up to me, the use of crypto is not a good thing. Every time you want to exchange secretly, of course, if you use crypto, it means that you send noise, because crypto encrypted stuff is just noise. Very high, large entropy profile. So, of course, you focus attention. Up to me, you have to add transmission security, for example, steganography. So, in fact, from a very general point of view, we just select some weak nodes. So the weakness issue may depend on your view. And we try to force the route through those infected nodes. So according to Diegeldin and some authors, in fact, there is a general interesting formula which has claimed that if you control m onion routers of a total of n, you can control this percentage of the traffic. So the aim is to increase the value of m and to reduce in a way or another the value of n. So we will infect m onion routers, and then we will try to decrease the value of n. I mean the number of onion routers through you can go through effectively. So the general description of the attack, you can use a botnet. So I will say a botnet, but of course you can use several small botnets in order first to infect some nodes and then to deny, to block, or to congest the other one. So it is a general scheme. Of course, Sean will present in more details. So we have, among many information, in fact, we have developed in our school a test network architecture, which is rather close to the reality, at least statistically speaking. And we have validated everything on this architecture. Some parts have been validated on the real network, and Sean will make experiment using the real network. We are not connecting to our architecture. And the question is, can we trust the Tor network? Or, well, I will say the things differently. Is it possible for a country to exploit the weaknesses that we have mentioned in order to, not to block Tor, but to control? So, from a general point of view, step one, you just identify, it is an intelligent step. You identify a subset of weak onion routers. You install dynamic trapdoors and so on. You modify the AES in contour mode in order to fix the initialization vector. And of course, we do not modify the OR integrity. Everything is in memory. And after that, we try to selectively deny access to the onion router we did not manage to infect or to control. So of course you have to establish a complete map of available nodes and then to deny according to 3 different techniques. So you will find on the website complete Google Earth map with all the different nodes, so I won't show it here. But in fact we have identified slightly more than 9,000 onion routers.
Over 9,000?
And, well, you have the description here. So we have observed that nearly 60% of OR are in the EU, while slightly less than 13% are in Asia. So once again, there is a complete map. Either they are under Windows, Linux, or it is hidden or not.
I can see from here.
So election now.
Tor works with, we have what we call bridges and we have relays, as explained at the talk yesterday. So the bridges are supposed to be like a way to prevent countries or governments or the adversaries from denying access to Tor completely. So, but then there's always a way, like, so there's a way for users to actually get the bridges, which is also a way for the very same attackers to get the bridges. So the normal ways to obtain the bridges would be from the website, the bridges website, or sending an email, or there might also be other social ways to actually receive bridges. So the Tor software actually provides a control protocol to enable you to script it or to actually communicate with Tor directly, build circuits or make requests, attach streams. You can do almost anything with it. So we have extended the Ruby controller for Tor that is normally used to build circuits or just to connect to Tor. So you can actually make requests with the library and do a couple of other things with it. So normally it's possible to get just 3 bridges at a time from any IP address you go to. Then probably after an hour or so, you might be able to get more bridges as another 3, but you get only 3 at a particular point. So with this library, you'll be able to request more bridges using Tor exit nodes. We're able to obtain about 70 in 10 minutes, and 70 distinct addresses in 10 minutes, and about over 200 in just 1 hour. So our goal was not to get all the bridges, we just tried, and then you actually obtain over 200 bridges within the time using this short script. So I can give a demo about how this is being done. So yeah, I have. So I've just connected to the control ports to show, so you can actually see some of the events that will come up as when I run the library. So this. Oh. Sorry about that. Okay. So yeah, I'm going to run RV. This would just connect, this would do this 20 times using different circuits, and if the circuit is not built in 3 seconds, it will just try to get the bridge either way and then continue. It could probably be done faster, or some circuits may not be actually completed in 3 seconds, so it's just a sample. The first part of the script I ran was just to get fast exit nodes and fast guard nodes to use for the circuits. And then the script I'm going to run is just picking anyone at random. I'm not selecting any particular entry node or exit node. Then the exit node is, I'm going from 0 to 20. Just pick the first 20 fast exit nodes. You can actually see as it tries to build the circuit, and when you see this succeeded, then you know it probably got, okay, it doesn't come back. So yeah, it has put the first 3 bridges it got, and it's keep trying. Has gotten 6. But right now, this has also been limited, so it doesn't get all the nodes immediately. So the bucket of bridges that it gives out using exit nodes has been limited for this reason. So that. But then, if we actually keep going, or you use all the exit nodes, you should be able to get a large number of bridges normally, just not now. So the library is actually easy for just about anybody to use, and it's easy for anybody to script through the pages. So then the vulnerability with the descriptors, the cache descriptors are actually distributed to just about every node. You have over 2,000 relay addresses that are actually there, and then it's like you give an arcade a list of 2,000 addresses and you tell them, okay, check if these addresses are vulnerable to anything. Of course, you might have 0-day vulnerabilities, and then you have a number of them that might be weak and very easy to compromise, and including Windows and Apple nodes, which might be easy for an attacker to infect with malware to use for the attack. So then the vulnerability scanning shows that about 30% of the ORs are vulnerable, 41% of which are Windows, and 19.6% run a Unix flavor. And this is in terms of the number of the nodes. And the percentages are likely underestimated. Well, about 20% of them actually have critical severity, but it's what is to be expected of a voluntary-based network. It might be beneficial if there was a way to actually tell clients or volunteers that, okay, your system might be vulnerable to this, or it just runs a test, and then it knows what exactly it can do to help, so it doesn't get attacked by an adversary. So the goal of the attack was to try to force a client to go through 3 specific nodes. That's, you're not trying to block the Tor network completely, but you just want to control it within a limited time when the cryptographic backdoor will be in place. So you would have to use a number of availability attacks. It could be similar to the Great Firewall, you resetting the clients. Most of all these availability attacks will only work if you have the complete list of the network already. So you still need all the bridges and all the public URLs that are available. And with the rate at which the relays actually change addresses, DHCP, you need to keep this list updated to have the attack work. So then another way would be you could actually spin packets on the network or have a kind of congestion just to exhaust the bandwidth on some of these nodes. So, previous attacks have been based on the congestion approach or even the packet spinning. you sending packets to multiple nodes at the same to multiple nodes in the Tor network. And with Tor, it used to be possible to actually build very long circuits. You could build a circuit of, say, 90 nodes. You have errors in your logs if the client actually checks it, but then how many users actually check their logs frequently when they use Tor? Most people, you probably prefer the GUI, just click a button with Vadilla, and then you connect, and that's about all. So, by default, Tor will choose the fast nodes and nodes that have high uptime based on the metric. But then this metric is also published in the consensus. Your bandwidth is there. It's like you tell the attacker, okay, this is how much packets you need to send to keep these nodes really busy. And then if I can send a packet through your node, say 10 times, the same node as I build a circuit of 3 nodes, and I cycle through that 3 nodes, say 10 times, it just keeps going. It has a multiplicative effect on the size of the packet I'm actually sending. So the goal of this would just be to keep the packets in place, just to occupy these nodes, prevent them from having time for other nodes, for other requests from the clients. And then again, it's not going to be played like all the time. You don't need to attack all these nodes at all times of the day. You're just trying to control them. Say, today you want to implement you have the dynamic cryptographic backdoor, and then you know the specific time or specific day that it will come to pass. Some countries might decide, or some governments might decide to actually try this at that specific time. Of course, the Tor metrics you see downtime in the number of clients connecting at that particular time, or it may appear as if the say country or government is throttling the network for the users. Users just won't connect to the specific nodes at that particular time. And then the attacker just has to, either he has pre-compromised nodes on the network, or he has a botnet, or other nodes he's able to compromise and install the malware. So long as you have all these nodes in place, they work normally at all times. At all other times, they work normally, but then at the specific time when it will be attacked, the client will only be able to connect to these specific nodes. So, and then this can also be set in a different way, such that the attacker can actually distribute the map to, say, different nodes, and then he has a map of nodes he wants to block at a specific time, and then he sends packets and just keeps the packets in play, keep building circuits, and then it just keeps going on and on. So yeah, I said I was going to demonstrate how the long circuit or the packet spinner works. So yeah, I'm going to pick a circuit of 3 random nodes and then build a circuit of 15 nodes. That's 5 loops over those 3 nodes. The random nodes might not always perform as the attacker wants, because some nodes will actually have different access requests or different access policies that will prevent you from making circuits with the next node you're trying to, or the next hop you're trying. But then here we can see this is the first node. This is it again. This is the second loop. This is the third. This is the fourth, and this is the fifth. So I can also show that we can browse through this. So yeah, I'm using Calico with this. Yeah. So I'm going to try to I disabled the auto attach mechanism of Tor. Yeah, we can see. Okay, right now the circuit has been closed. So I'll have to rebuild the circuit before I try this again. But then again, this doesn't work with the new version of Tor anymore. But then, if you use the old client, it still works. So, but there have been mechanisms in place to prevent this, but then it just can't be put to use until all clients, everybody that uses Tor, has upgraded their versions. Okay, maybe I could get back to this after. The circuit has been closed again, so maybe I'll just do this after. So then for the TCP resets, it's not a new thing, resetting packets or blocking nodes. The whole attack is based on you using just about any availability attack that is out there, your resets or ways to congest the network. So the resets has been there. Some ISPs use this to prevent clients from accessing some services or different ports. So unlike your typical reset where you have to send reset packet both ways, for Tor, you just need to send reset packets just to the client that is trying to connect, and then even if the relay sends the packet back to the client rejects it and it tries to pick a different relay. So this will go on until he probably picks your malicious node which you have in place. So you still have to rely on the randomness of Tor to select those nodes that are vulnerable. So the other thing would be if the client tries to build a circuit using first the entry, probably a malicious node, and then the next one isn't malicious, you might want to block that also. So that can be done from the nodes you've already compromised using just about anything. So then the whole attack will be in this form where you have the botnets infect. You deny access to some nodes that you are not able to infect using whatever means you have. You could do the reset. It could be some other forms of denial of service attacks, and then you have ISPs also doing the reset attacks to the clients. And the denial of service attacks will continue until the client uses the nodes you want him to use. So, alternatively, you might not need to.
Could you move up your microphone?
Okay. Alternatively, you may not need to block access to all the nodes, but then just the ones with higher bandwidth or higher metrics than the ones you have on the network. So you might have some nodes on the network already that have high bandwidth or with an high uptime. Uptime is not really a problem. You just need to leave your nodes connected until when you need it to work. So, but then the bandwidth might be the question, because you need more nodes with bandwidths. And then the attack continues the same way. So then the second version of the library also allows you to build circuits in circuits, instead of just building one single long circuit. So with the new version of Tor, you are only able to build a circuit with 3 nodes. So, but then if I want to build a circuit and still have the multiplication effects of sending packets through this, I'll have a circuit going through another circuit and then a third one, and it could also go in the same way however you want it to. So the drawback with this is the exit nodes must be chosen carefully so they don't have like restrictions to the next hop. That's the next entry node you're trying to connect to. So sometimes your entry node might be on port 9001 or some other ports. That's the URL port. But then you have to choose exit nodes that allow access to the next hop. And you can actually an attacker can actually send packets using either of all these proxies, just to increase the congestion.
So just a few words about the malware we have developed. So it is very complex code implementing a lot of things. So of course, since we are able to deploy malware, we can fix the key. Of course, it is in constant time to decrypt since we know the key in advance. But generally, it's more efficient in this case, precise case, just to fix the IV. And then the decryption and the detection of weak ciphertext is in polynomial time. So once again, there is a library that we have developed in order to detect and break. It is possible, we have developed a lot of optimization techniques. For example, if we have only one single file with plain text tagging techniques and so on, and if you use in the library the detect single file.c, you will see how it works. So it is possible, of course, to make a lot of things. And the malware is able to adapt to the fact that, in fact, since we only force routes through infected node with a high probability, it may appear that, in fact, since the probability is not close to 1, that it cannot, some keys remain uncontrolled, so he is able to detect that and just to say, okay, I do nothing. Okay, it is only small bricks that then you have to combine in a very random way, according to your scenario. It is just a framework, attack framework. You can replay it, change the time window, everything is possible. And once again, everything is in memory. We do not modify the settings. Well, from a more general point of view, of course, but if you know many of the nodes, you could simply block them, but, well, it is not our intention. We just want to show that it would be possible to bypass crypto by some sort of surveillance and monitoring. So, once again, the discussion is, and I totally agree that it is, of course, impossible to have the exact figure. It is not exact science to have the exact figure of success probability. But, well, even if we manage to break at least 10% or even 1% of the encrypted traffic, up to me, it cannot be accepted. So, well, once again, I will stress on some very critical point up to me. It is very surprising to see that, in fact, there is no high-level auditing of our security. The volunteering is very nice, but if everyone does what he wants without control and security control, well, the security of the whole infrastructure is limited to the unsecurity of a few ones. So it is not possible. And of course, when you have many vulnerabilities and flaws, well, it's very easy to infect. Without giving too many details, we have been very surprised, not to say shocked, that, for example, HTTPS machine was so badly configured that it was possible to catch the secret key instead of the public key. So I'm not sure it's a good thing. Of course, once again, I'm convinced that using cryptography alone is not a good thing. You send noise. And if you send noise, it means that you have something to hide. So up to me, steganography or other transect security tools are far better. And of course, using TCP, you know what you may find. So we hope, of course, since our work, for example, the spinning attack has now a limited effect. So we're happy to see that, in fact, we have somehow contributed to better security for Tor. I think that some measure in order to maintain the activity of Tor and to enable far better security, I think, yes, forbid Windows Onion Router, well, it's maybe a little bit drastic. But in fact, it would be nice maybe to enforce some scanning, to use some scanning tools, and to deliver some security certificate for Onion routers. Okay, you are valid for the service, you can go on and join the group. But I'm convinced that it is very mandatory to detect weak hours. To be clear, an attack cannot work if all Onion routers cannot be infected. But we are very far from this situation. So that's why I think that part of the solution, the most part of the solution, is to enforce some high-level security policy managed by the Tor Foundation to manage the security of all routers. And of course, prevent scripting, since part of the security relied on the fact that some relay bridge were hidden. Well, prevent scripting in a way or another. So, as a conclusion, in fact, well, you have a number of comments, but I will stress on one fact, that less and less sophisticated attacks will be the fact of a single step. You will have multiple innocent-looking surgical strike, little touch, whose combination will produce final effect. I had the occasion since 2 years to analyze some sophisticated attacks, mostly coming apparently from China. Well, just deploying one single malware, I think it's over. Now I just change a part in memory, I send a document, and so on. And the combination of all those effects makes the final attack. And of course, from the victim point of view, it is quite impossible to prevent, quite impossible to detect. For the single reason is a combinatorial effect. How to survey, to monitor, to compare everything. So it is impossible. And of course, if you want to design trapdoor or backdoors, you have to do the same, just to split everything in multiple innocent-looking parts. So, well, midterm works. We hope that Infaction will go for a PhD on that subject. But I think that using steganography, to have some sort of steganography version of Tor would be nice. To enforce some memory protection, we are actually working for different companies about techniques to prevent attacks in memory. And once again, I would like to stress on that point, just enforce our high-level security policy. So, maybe you want to make some comment?
No.
So, in fact, it is some change that appeared recently, and Sean, if you want to.
On the Tor project website, we can see the draft for future crypto proposals. Well, the main thing is, I think, since it's modification of the keys in memory, the fix could actually be done by the operating system or even the crypto APIs developers, so that they prevent such attacks by the malwares. But then again, the application developers should also consider protecting their applications against such attacks, pending the time when the API developers release such fixes. So if there are memory protection techniques, they would be able to prevent such malwares from affecting their applications. And Tor being a critical application, something should be done to protect this in the memory. And then for the congestion attacks, there's a paper about the comparison of datagram, which could be a start. Since UDP might not have the same congestion problems as TCP, but then it could still have its own security vulnerabilities in the end. So that's about all. Thank you. Questions?
Well, thank you very much for that talk. And I would also like to remind you to use the feedback system on the talk. Feedback system is available in the Fahrplan if you select that talk. Now we still have time for Q&A session. Could you please raise your hand if you have a question? We'll start at the back of... Okay. There we go. Okay.
So you said that there were 30% vulnerable relays. The Tor protocol balances load by using the faster relays more often than the slower ones. And in fact, the Tor network has about 2,500 relays now, and a small number of them are very fast, and the rest of them are quite slow. So I would not be surprised to learn that the 30% of the relays that you consider vulnerable are less than 1% of the network by capacity. And once you are only compromising a small amount of the network, that requires you to do a much larger denial of service attack against the rest of the network to make your attack work. So I guess my question is, what fraction of the network by capacity do you believe is vulnerable? Not just fraction of the network by relays.
No, it's a very important question, but it's difficult to evaluate without making experiment on the real network.